Y17, Maxwell's equations. Let us first consider two Gauss laws. The first Gauss law is for the electric field, and you recall the electric field due to the distribution of charges over space is just this expressed in terms of this three-dimensional integral, and this charge dq can be expressed as charge density over space multiplied by the volume element, differential volume element over space. And this R is actually more accurately expressed in terms of x minus x prime absolute value integrated over space. Wait a second, there is something wrong. This is the electric field. So it is not only charge, and we have to multiply the unit vector. And this unit vector is ER hat, and this one is actually the displacement from x prime is the position of the source charged particle, and x is the field point. Okay. Okay, so if we integrate this electric field multiplied by the differential surface area and integrate over this closed surface surrounding a charge distribution over space, then the value is equal to the charge enclosed by the closed surface divided by permittivity constant of the vacuum. And the charge can be expressed as the integral over space multiplied by the charge density over space. If we apply the divergence theorem, the surface integral over a closed surface can always be expressed as a volume integral over the volume that is enclosed by the closed surface. And right hand side, we have a volume integral of charge density. We can move this right hand side to the left hand side, then the integrand becomes a divergence of the electric field subtracted by density over epsilon zero integrated over space. If you shrink this volume into a very tiny volume, then the integrand becomes a constant. In that case, we can pull this integrand out of the integral. Still, this volume is vanishingly small. However, it's not equal to zero. However, therefore, we can divide this both sides from. As a result, at every point, divergence of the electric field is the density at that position divided by permittivity of the vacuum. This is the Gauss law for the electric field. We can think of the Gauss law for magnetic field too. In here, in the case of the electric field, charge density is either positive or negative because there is an electric monopole. Charge can be either positive or negative. However, in the case of magnetic field, rho m magnetic charge density is always 0. Why? Any magnet consists of North Pole and South Pole. If you divide this magnet into two pieces, North Pole and South Pole doesn't separate. Instead, South Pole is created in here, North Pole is created in here. So always the sum of North Pole and South Pole becomes 0. Therefore, there is if we make use of the fact that there is no magnetic monopole, the right-hand side is always 0. Applying the same method by making use of the divergence theorem, we conclude that divergence of the magnetic field is always 0. So we have two divergence of electric field, density, charge density over epsilon 0. Divergence of the magnetic field is 0. These are two Gauss law for electric field and magnetic field. And this is called the differential form, and this is for the integral form. So we already learned two Maxwell's equations. Now we learn the other two Maxwell's equations. The third Maxwell's equation is called the Faraday's law. And we know the electric field, usually electric field is irrotational. Because of this, we can define the potential, and the potential's minus gradient is always electric field. In this case, electric field integrated over a closed path is always 0. This is a conservative force. However, this is true only if the steady state means there is no time dependence. If there is a time dependence in the magnetic field or magnetic field flux passing through a circuit, this is not true anymore. So the conservativeness of the electric field is not true anymore. Instead, the conservative force is not isolated to the electric field. Instead, it is distributed over both the electric field and magnetic field. So we have a more general conservation theory that includes both electric and magnetic field. Let's see. The magnetic field flux can be expressed as the integral over surface of the magnetic field. If you take the total time derivative of the magnetic field flux, this differential operator enters into the integrand. It becomes the partial time derivative because spatial part is included only in here. Now, this is a line integral over a closed path. It is always expressed as a surface integral if we apply Stokes' theorem that we learned already. So this is a surface integral of a curl of the electric field, and right-hand side is also a surface integral. Why don't we combine these two integrals by moving the right-hand side to the left-hand side, and then shrink the surface to be a very tiny surface that can be approximated as a single point. In that case, again, we can pull out this integrand that is almost constant and becomes a scalar product with the surface element is vanishingly small, but it is not 0. So we can divide this one in each component. For example, x, y, z component. Every component must vanish. This must vanish at for any XYZ component. As a result, this Faraday's law leads to the differential equation. The curl of the electric field is a negative of the time derivative, partial time derivative of the magnetic field. Now we learn 3 among 4 Maxwell's equations. The next one is closely related to Ampere's law. The magnetic field integrated over a closed path is expressed as a current passing through that circuit. That is called Ampere's law. And this current can always be expressed as the surface integral of a current density. Now we again make use of Stokes' theorem to express this line integral as a curl of the surface integral. Again, with a similar manner, we find that the integrand factors out if we shrink the surface into a very tiny surface. As a result, we obtain the differential form of the Ampere's law. So why don't we compare this one with the counterpart, that is the curl of the electric field expressed and in terms of time derivative of magnetic field with negative sign. Maxwell found there is something missing. I mean, for example, in the divergence case, electric field rho over epsilon 0, magnetic field divergence was 0. For example, if we remove any charged particle in space, for example, that is just a vacuum between the sun and earth, still electromagnetic field that is called light travels from sun to earth. So in that case, we can remove this one to replace this one with the 0. So electric field, magnetic field, they have the common equation. They are symmetric, very much symmetric. That symmetry was found by whom? As well as Maxwell, the Heaviside, who introduced this vector notation, found there is a symmetry. If you replace the electric field with C times magnetic field, C times C, here C is the speed of light, CB is replaced with the minus electric field, then everything must be the same. That is the dual symmetry of the electromagnetic field. So why don't we replace this with this dual symmetry? Then E becomes a CB and negative sign, keep the negative sign, CB. So CB, CT. So CB is replaced with E, so this one becomes a plus and 1 over C time derivative of the electric field. So Maxwell claimed that there should be another equation satisfies the time derivative of the electric field that generates the curl of the magnetic field, as well as the actual current along a wire. So this is called the displacement current. Let's see what's happening. So divide this one, this speed of light on both sides, you will find 1 over C squared in here. And actually, if you solve the 4 Maxwell's equation altogether, you will find that the propagation of the electromagnetic field is moving with the speed of light. That was first found by Maxwell. And by the time Maxwell studied these equations, mu 0 and epsilon 0, that determines the strength of the electromagnetic field, was known very well. And the speed of light was also known with a little bit larger uncertainty relative to what we know. By accident, he found that this should be the speed of light. And actually, the numerical value for this permeability constant and permittivity constant provided him to find that it is exactly the same as 1 over speed of light squared. So because of the symmetry that Maxwell and Heaviside found, it was possible for them to construct a fully symmetric theory for the electromagnetic field. Let us look at the displacement current we just learned. In fact, current flowing along a wire, this is the actual current, is a rho times V is a current density, and current density integrated over a surface should be a current. We know very well, based on the Ampere's law, magnetic field is generated around current flow. However, time variation of the electric field can also create the magnetic field. How? Why don't we think about a parallel plate capacitor? Current I flows in, flows out. In the middle, this is a vacuum, nothing. There is no current at all. However, the electric field, we know the electric field that is along the unit vector E3, and in between the two plates, it is a sigma over epsilon 0. Okay, so this electric field is proportional to the charge density. This charge density is a charge divided by the cross-sectional area. Why don't we take the time derivative of this? What's that? dq over dt, that is the current. Okay, so the current is identical to the time derivative of the charge density, except that this is I over A. I over A, what's that? That is a current density instead of current, because we have divided the current by the cross-sectional area. However, this is not a real current because there is no charged particle moving between the two plates. So Maxwell attached the D, that is the displacement current. Displacement current is nothing to do with the actual motion of electric charge. Instead, it is closely related to the sigma. That sigma is what? Sigma is epsilon 0 E. And sigma's time derivative means time derivative of electric field multiplied by epsilon 0. Oh, this is that. Displacement current density is acting the same role as actual current density, but it is expressed in terms of epsilon 0 multiplied by the time derivative of the electric field. Okay, if you apply divergence of curve B, so this is symmetric and this is anti-symmetric, it is always a 0. So you will find the divergence J in here, this is a 0, and divergence E, what's that? That is rho over epsilon 0. Epsilon 0 cancels. You will find a continuity equation. If there is a current flowing in, and if there is no current, current flows in and no current at all, then there is an accumulation of electric charge. Therefore, divergence J plus time derivative of charge density sum of this is 0. Okay, so here divergence J is non-zero because it is not continuous. Current is not continuous. There is a discontinuity of current. Current flows in and no current flowing out. So there is accumulation of charge that leads to the time, a non-vanishing time derivative of charge distribution. So this is a general form of the conservation theory of the electric charge. Now we have constructed the final theory. Ampere's law was found to be incomplete, and only if we include the Maxwell's law that corresponds to the displacement current, we can find the most general form for the equation of magnetic field. So resultant, the last equation for the Maxwell's equation is Maxwell-Ampere's law. If you remove this, this is Ampere's law, but that is an incomplete theory, and only if we include the displacement current density, we have a complete theory for the magnetic field. Now we have learned all of the electromagnetic theory that is expressed as a four equation of Maxwell's equation. Last, we review what we learned for the displacement current. This is the actual current flow of electric charges moving along a single direction inside a wire. In here, there is no actual motion of the electric charge. Instead, there is an accumulation of positively charged particle on a plate and accumulation of negative charged particle on this plate, and this charge amount is increasing as time goes by. Minus q, magnitude of minus q also increases. Then between the two plates, even though there is no actual motion of electric charge, there is a change in the electric field. The change in the electric field multiplied by permittivity constant is and integrated over surface. It is a displacement current, and this is a displacement current density. Okay, and both actual current and the change in the electric field behaves as a source of the magnetic field. So magnetic field can be created from the actual current, and in addition, it can be created by the changing electric field. So displacement current in a capacitor can be studied in this way, and I think you can follow with these for this derivation. So in summary, we learned four Maxwell's equations. Integral form is on the left and differential form is on the right. These two are Gauss law. No, these two are Gauss law. And this is using divergence theorem, we can construct the corresponding differential form of the Gauss law. And this is a Faraday's law, differential form of the Faraday's law. And this is Ampere's law, and including the displacement current, we can construct Maxwell-Ampere's law. And the differential form for the Maxwell-Ampere's law is given in here. Now, let us review the simple vector algebra. For any vector field, we can compute curl and apply the scalar product. It looks like a triple scalar product. We have two operators of the same shape. In that case, triple scalar product is anti-commutative under exchange of any two objects. However, these two are symmetric objects. Therefore, the answer must be 0. So divergence of curl is always 0. For any scalar field, gradient curl of the gradient is also vanishing because this cross product is anti-commutative, but these two operators are identical to each other, so curl of the gradient is always 0. We recall that the Gauss law for the magnetic field is divergence B equals 0. If I apply this fact, then divergence B equals 0. Okay, there always exists a vector field that is called the magnetic vector potential. Magnetic vector potential gives a magnetic field. Why? Our requirement by the Gauss law states that divergence B equals 0. For any vector field, curl of A must be magnetic field because divergence of curl is mathematical identity. This is a 0. So for any magnetic field, there exists a vector field whose curl is the magnetic field. Okay, let us rewrite Faraday's law. Faraday's law is like that. Why don't we substitute the expression for the magnetic field in terms of the magnetic vector potential A? That is curl A. And move this one to the left-hand side. What you find is curl of electric field and time derivative of magnetic vector potential. You know, curl of something is a 0 if gradient. Curl gradient is always 0. So this must be 0. That means electric field plus time derivative of magnetic vector potential must be expressed as a gradient. So simplest choice is a minus gradient that is always used for the electrostatic case. As a result, if I move this one to the right-hand side, electric field is originally expressed in terms of the minus gradient of the electrostatic potential. However, electric field can also be produced by changing magnetic field according to Faraday's law. That is expressed as the time derivative of the magnetic vector potential. Okay, finally we can consider gauge invariance. Gauge, the electromagnetic field, can be expressed in terms of the scalar potential phi and magnetic vector potential A. However, these potentials are not uniquely defined. There are many possibilities that give the same physical field called electric field and magnetic field. This is called the gauge invariance. And you know, mgh is the gravitational potential, but you can always add 10 joule or something like that. Any constant can be added. But in here, electromagnetic potential is much more complicated than this. However, it is the concept that there are many candidates for the electrostatic potential and magnetic vector potential. Both of them are possible. Both of them has many candidates. Suppose that we can make a transformation from a magnetic vector potential and choose another. And if you shift the magnetic vector potential by this, substituting in here, you will find curl of gradient is always a zero. So addition of gradient of a scalar field to the magnetic vector potential doesn't change the magnetic field at all. Aha, so we have a freedom to choose the magnetic vector potential by adding arbitrary gradient of a scalar field. Using in this similar manner, we can also transform the electrostatic potential. Why don't we substitute phi prime and a prime to compute the electric field? Then we find these three terms. In here, this is the original one, and this is additional contribution. Now we find that this time derivative vector potential is the same as the original one, the same as this one. However, we find this term, to have the same electric field, what we have to do is this phi prime plus time derivative of this scalar field must be the same as the original scalar field. As a result, this scalar potential and magnetic vector potential can be shifted to another value, but that is not arbitrary. Instead, there exists a scalar field chi, and its gradient can be added. When gradient is added to a vector potential, electrostatic potential should be subtracted by the time derivative of the scalar field. So this is the most general form of the gauge transformation. This gauge transformation doesn't change the physical electromagnetic field. Orbital magnetic dipole moment of an electron, when electron travels along an orbital motion, then it will create a current, and there should be a cross-sectional area. In that case, you will find the magnetic dipole moment. That magnetic dipole moment is cross-sectional area multiplied by the current. In this way, we can estimate the size of the dipole moment of an electron. However, in fact, is not exactly the same. Instead, there are many values allowed. There are multiple values. This is just a common factor that we learned from this AI. However, there are multiple values allowed. This cannot be explained in classical electrodynamics. It is an absolutely new concept that comes only from quantum mechanics, and that is found to be the fact. In addition, the Bohr magneton is just the interpretation of cross-sectional area multiplied by current. So you can follow this simple calculation. In addition, there is a spin magnetic moment. That means electron that does not travel, that is standing still has a magnet. It is an absolutely new idea. But Wolfgang Pauli found that there is a magnetic dipole moment of a single electron that is not traveling, that is standing still. And furthermore, its magnitude of the magnet of the electron is twice the value of the spin. And twice the value of the spin, then that unit is the same in both cases. Later, when we learn quantum mechanics, we will learn more detail about this.